Okay, so we are talking about cosets. Basically, we have defined the left coset of a group of a subgroup of a G. So again, let us just recap. Let G be a group. Let G be a group, and H is a subset of G, which is also a subgroup. Say H is a subgroup of G. So this is a group. And this is a subgroup of G. Okay. Now, we take an element A from G, and then we define that AH, this is the left coset is as AH, which is H is coming from H. Okay, this is how we define the left coset. This is called left coset. Now, this we define for all the elements. Now, in the last class we have seen if A is coming from H, then we have seen H H is nothing but H. This is giving us the same set if we choose the H from this set, A from this set. Now, if we choose A from the outside of this, okay, then we want to see whether this has a common point or not. So, then we want to define this has a common point or not if it is outside this set. Okay. So, that we want to see. So, that let us just try to see that. So, let us just define this theorem. Let G be a group and H be a subgroup of G. Okay. And let A is coming from G minus H. So, this is our G, this is our H. Now, if we choose a F outside H, then our claim is H, this is empty set. So, that means, if we denote this by H, so they have no common point. So, they are disjoint, we want to prove that. We have seen that if we choose this A from H, that will give us basically H, that HH, small h. But now, the claim is if we choose an element outside H, then these two sets are disjoint. Okay. Sorry. Now, how to prove this? Then this is the theorem, statement of the theorem. Now, how to prove this? Okay, so, to prove this, suppose they are not disjoint, suppose there is an element P in there which is common to them. Now, suppose if possible, let this there exists an element, we will reach to a contradiction that such element is not possible. So, this implies what? This implies P is in AH and P is in H. So, P is in H means P will be some AH1. Okay. Now, this implies H1 will be equal to P H1. So, this implies A is equal to P H1 inverse. Now, P is in H, H1 is in so H1 is in H. So, H1 inverse is also will be in H, because H is a subgroup. Now, P is in H. So, they are composite, they are product means that star operation. So, this will also belongs to H, because H is a subgroup. So, closure property. So, this which belongs to H, which is a contradiction, because we have taken A to be not belongs to H. So, this is a contradiction. So, that means this is true. So, they are disjoint. Okay. So, if you choose a element from outside this, then they are disjoint. Okay. Now, we want to see if we take two coset, left coset H, BH. So, we will see either they are disjoint or they are same. So, that is another result we will see. So, if you take two element, another element B, then if we consider BH, then we will see either they are same or they are disjoint. So, that will leads to us a equivalence relation. We will come to that slowly. Okay, so this is another theorem on the coset, left coset. So, again G be a group and H is a subgroup of G. I am not writing the details of this statement, subgroup of G, and let A B be any two element in G. Then either of this is true, then either AH equal to BH or AH intersection BH is empty. Either these two sets are same or they are disjoint. Okay. So, this is the statement of this theorem. Now, how to prove this? So, we have this set, we have AH, so AH and we have BH. So, we are telling this is not possible. So, they are either they are same or they are disjoint. So, there are two possibilities. If they are disjoint, then fine. If they are not disjoint, if there is a common element, let they are not disjoint. Suppose AH intersection BH is not empty, then we will see, we will show that A is equal to BH. Okay. So, how to proceed? Now, so that means there exists a or there exists a P belongs to their common, because they are not disjoint. So, this implies, so we will wrap this. Okay. So, this implies P belongs to H and also P belongs to BH. So, P belongs to H means P will be written as some AH1 which is same as BH2, some other H2. Okay. So, this implies A will be written as PH1 inverse and B will be written as PH2 inverse. Now, we need to show that these two sets are same. So, we need to show that AH equal to BH. So, for that we need to take an element from here and we need to show that is an element from here. So, this is a subset of this, again we need to take an element from here, we need to show this is an element of here. So, let us take an element from this set. So, let x belongs to H. So, this implies x will be written as some A H2, H2 is we have already used. Okay. So, now this is basically, we know the A is basically P of so this is basically AH2. So, this is basically P of some, so A we know A is H1 inverse, A is 3. So, which is same as, so H2 which is P. So, P is now same as BH2, B of H2, H1 inverse H3. Now, this is nothing but another H4. So, B H4. So, this means this belongs to BH. So, if you take an element from H, we can see this is an element in BH, and reverse also we can show. So, this means H equal to BH. So, if they are not disjoint, then they has to be same. Okay. So, that is the proof. So, that means either they are same or they are disjoint. So, either one of this is true, either they are same or they are disjoint. So, this leads to us a like relation we defined. So, if they are same, we defined A is related to B, okay. And we will see which property will give us that. So, let us define a relation. So, we will just before that we will just have another theorem. So, when they are same, that we want to know. So, that means when AH equal to BH, if there is a condition that they will be same. So, let G be a group and H be a subgroup of G, then H equal to BH. So, we know either they are disjoint or they are same. Now, we are interested to know when they will be same. If and only if, this is a necessary and sufficient condition, if and only if this condition is happening, A inverse star B belongs to H. Okay. So, this is the necessary sufficient condition for. Now, proof is simple. So, proof has two parts. So, we assume these are same, we take H equal to BH. So, that means this will give us what? So, that means H1 equal B equal to some BH2 always. So, now if we take the inverse, so this will give us what? This will give us, now what is A inverse B? A inverse B is now, A is this one and B is this one. So, A inverse B is, so A inverse we can take from here. So, A is basically, if we just apply B H to H1 inverse, or we can just write B to be like this. So, this implies B is basically A H1 H2 inverse. So, A inverse B is basically A inverse A H1 H2 inverse. So, which is basically H1 H2 inverse, which is nothing but an element in H, because H is a subgroup. So, that means this belongs to H if these two are same. Now, conversely, if this is true, then we have to show these two are same. So, how to show that? Now, suppose conversely, suppose A inverse B is belongs to H. So, that means this will be some H1 say, we have used H1 H2 and it may be H3. So, then we need to show AH equal to BH. So, that is quite obvious, because then then B is basically, if we apply A on both sides, A is 3. So, B belongs to AH. Okay. So, now, so we can formally prove that A is equal to BH. So, how to show that? So, we have to take an element from here, we have to show this is an element of here. So, if we take an element from here, so that is x equal to some A H4. Okay. Now, A is nothing but B H3 inverse. So, this is basically B H3 inverse H4. So, this belongs to BH. So, if you take an element from H, we can show this is an element from BH. Now, other way around we can show, we can take an element from B H, we can show this is an element in A H. So, this is the proof. So, that means, if this condition satisfy, then A H equal to B H. Okay. So, now this now we defined a equivalence relation between two elements in G. Basically, if they are in, so we know that if you take two element A B, then their coset is either same or they disjoint. So, if they same, then we say they are related. Okay. And by this theorem we can just say that. So, that this is the equivalent relation we are defining. So, again we have a set G, group, we have a subgroup H. Now, we take two elements from this is we are defining a relation. Now, we say A is related with B if and only if this is how we define this rho. This rho is a relation. This is the definition of rho. So, in other word, that means if and only if A H equal to B H, because the earlier theorem we have seen, if this is the necessary condition for A H equal to B H. But anyway, this is an equivalence relation. So, I will see this is an equivalence relation. So, this rho. So, we are telling, we take two elements, we are telling they will be related under this relation rho if A inverse B star B belongs to H, where H is a subgroup of G. Okay, now we will show this is an equivalent relation. For that we need to show the reflexive. Reflexive means A star A rho A, I mean that means A belongs to rho. So, now what is A star A? A star A is basically E. Now, E is an identity element and H is a group, subgroup. So, this must be belongs to this. So, this is reflexive. Now, what is symmetric? Symmetric means if we take A B belongs to rho, then we have to show B A belongs to rho. Now, A B belongs to rho means A inverse B belongs to H. Okay. Now, we need to show that B inverse A belongs to H also. Now, if we know this is belongs to H, now H is a group, subgroup, the inverse also belongs to H, inverse of this. So, this implies B inverse star A belongs to H. So, this implies B A belongs to H, B A belongs to rho. So, this is the symmetricity property of this. So, that means if A related to B, then B will be related to A. This is the symmetric property of this. Now, we need to show the transitivity, whether rho is transitive or not. Then we can say rho is an equivalent relation and then we can have a partition on this set. Okay. So, transitive means if A is related to B and B is related to C, then we need to show A is related to C. So, now this means A inverse B belongs to H and this means B inverse C belongs to H. Now, this is the star. Now, if this is belongs to H, this is belongs to H, then we can compose these two, then A inverse B, this is the. So, this implies by associativity property A inverse C belongs to H. So, this implies A is related to C, small c. So, transitivity property is satisfying. So, that means rho is an equivalence relation, Okay. So, now if rho is an equivalence relation, then it will partition the group in a equivalence classes, partition the set in equivalence classes. So, basically we have a set G, where we have defined a equivalence relation rho, A is related with B if they form a same class of coset, if their coset is same. So, that means, if this belongs to H, then we say they are related. So, that means they will form a partition on this G. We know every equivalence class, equivalence relation form a partition, and those are called equivalence classes. So, we take an element here. So, class of A is nothing but set of all x which are related with this under this equivalence relation. So, that means A is related with x. So, that means A inverse x is belongs to H. Okay. So, this means this is the set of all x such that x belongs to H. So, this means this is H. So, this is the left coset. So, this equivalence classes will be the basically left coset, and we know this cosets are left cosets are disjoint, either they are same or they are disjoint. So, this will form a partition, this set of left coset will form a partition on this group G. Okay. So, now this will be this will form a partition on the G. So, now we will see this number of points in this cosets are same. So, the cardinality of two left coset are same. So, if you take two left coset, this is say AH, and if you take another left coset BH, now we will see that cardinality of H, the number of element in H is same as cardinality of BH. This we will prove. So, they have same number of elements. So, let us just try to prove this. So, this is again a theorem. This theorem is telling any two left coset cosets of H in G have the same cardinality. Or same number of elements. So, how to prove that? So, to prove that, so basically we take two left coset H B H. Now, how to prove they have same number of elements? If we can have a injective function from H to B H, then they are same. So, we define a function from H to B H like this, f of H is equal to B H for all H belongs to H. Okay. Now, we saw that this function is injective, then we are done, then they have same number of elements. So, how to show this is injective? For that we need to take two elements from here. So, AH1 is not equal to AH2, and then we need to show that f of AH1 is not equal to f of AH2. Suppose f of AH1 equal to f of AH2, if we assume this. So, this implies this is BH1 is equal to BH2, this is by definition of this function. Now, this implies H1 equal to H2, because B has a inverse, this is cancellation law. So, this implies AH1 equal to AH2. Okay. So, if so this implies f is injective function, injective. So, that means they have a same number of elements in both the left cosets. So, cardinality of this is same as cardinality of this, which is same as cardinality of some other left coset like this. So, all the left cosets have same number of element in it. Okay. So, now we will prove a theorem which is called Lagrange's which is by Lagrange. This is telling about the cardinality of a subset, and this is basically telling us the cardinality of subset. If G is a finite group, then the cardinality of subset, cardinality of any subset divides the group itself. Okay, so, just quickly Lagrange theorem. So, this theorem is telling order of a group, order means the cardinality of that group, order of every subgroup of a finite group G is divisor of G. Okay, this is telling us, suppose G is a group and H is a subgroup of G, and if G is finite, this is telling us order of H is divides order of G. Okay, so this is called Lagrange theorem. So, we have to prove that. So, any order of a subgroup divides the order of the group. Order means the cardinality. So, how to prove that? So, now so how to prove that? Now, suppose order of this group is n, say there are n element in this group G. Now, we know that there is a partition is basically the cosets. So, we know, suppose there are n cosets. So, there are elements from this group such that this is basically this is G. So, this is x 1 H, x 2 H like this, x m H, because we know this cosets will form a partition on this G. So, basically G is now union of x I H, I is from 1 to m, suppose there are m. Now, we know that each coset, just in the last theorem we have proved that each coset has same number of elements. Okay. And H is a coset, because H coset will give us E H, because E is same as H. So, H is also a coset. So, this is each coset has order of H. So, this means basically if you take the cardinality of G is basically m of cardinality of H. Now, this means cardinality of H divides cardinality of G, and this is happening because this is finite. If it is infinite, we cannot talk about this division. So, for any finite group, a subgroup, if we consider the size of the subgroup or the cardinal order of the subgroup divides the order of the group. Order means number of element in that group, the cardinality. Okay. So, this is the Lagrange theorem. Thank you.